The third set of notes dealing with stoichiometry is really an application of stoichiometry known as limiting reactant type questions. Now, limiting reactant, as well as any other stoichiometry, it's actually similar to a recipe. So to understand limiting reactants, I actually want to talk about building a simple cake. So we're going to use this simplistic cake recipe. Now, no, it won't work to make a cake, but we're going to pretend this makes one good tasting cake. Now, this is what the recipe calls for. 2 cups of flour, 1 cup of butter, a teaspoon of salt, and a half a cup of sugar. Now, if I want to make as many cakes as possible, I'd get my ingredients out of the cupboard, flour, butter, salt, and sugar, and I'd look at what I've got. Turns out I have 6 cups of flour, 4 cups of butter, 112 teaspoons of salt, and 429 cups of sugar. Now, from that information, how many cakes can I make? Well, you have to start evaluating based on the number of each ingredient and what's in the recipe, how many cakes could that make? Now, you can do some of these in your head quickly, and I think you'll quickly realize that there's a very specific number of cakes I can make because I'm going to run out of other ingredients. Now, mathematically, we want to look at this from a mathematical point of view. So what are you doing in your head? Well, that's my recipe, and that's what I've got uncovered. So let's take a look at the math. I have 6 cups of flour, and I want to know how many cakes I can make. So I don't want cups of flour, I want cakes. And the recipe is going to tell me how many I can what the numbers are here. So remember, in any dimensional analysis, I need 2 equivalent numbers. The recipe says for every 2 cups of flour, I get 1 cake. So 2 to 1 looks like 6 times 1 divided by 2. I can make 3 cakes from that much flour. Then I do the same thing for butter. I've got 4 cups of butter. I want to know how many cakes I can make. I don't want butter, I want cakes. And for every 1 cup of butter, I get 1 cake. So I can make 4 cakes based upon the butter. Looks like I can only make 3 cakes so far because I don't really have enough butter to make 4 cakes. So, or I'm sorry, I don't have enough flour to make 4 cakes. So far it looks like I can only make 3 cakes. And I'm going to run out of flour. Well, let's evaluate the other two. I also have salt and sugar. Well, I've got 112 teaspoons of salt in the cupboard, and I want to know how many cakes I can make from that. The recipe says for every 1 teaspoon of salt, I can make 1 cake. Well, that's 112 cakes. 3 is a whole lot less. Looks like I've got way too much salt. And then I do the same thing for sugar. I don't want cups of sugar. What I really want to know are cakes. And the recipe says for every 1/2, well, that's 0.5, I can make 1 cake. So 429 divided by 0.5 is 858. It looks like from that data, and this is something you may have picked up very, very quickly, even without doing all the math, looks like from that data, I can really only make 3 cakes. And it looks like I'm going to run out of flour. And once I run out of flour after making 3 cakes, I'm done making cakes. And it looks like there's still going to be butter and salt and sugar for me to put left or to put back in my cupboard. Well, that didn't seem too hard. Well, honestly, we use the exact same ideas when we're doing limiting reactant stuff in chemistry. Now, limiting reactant is the reactant that makes least. Think of alliteration here. Limiting makes less. That's a key idea. So if you can predict how much each could make using stoichiometry, the one that makes less is going to be your limiting reactant. And it controls everything about the reaction because it gets used up. There's nothing really magic about the limiting reactant, but it is the most important thing because once you use up that reactant, it's gone and the reaction must quit. I stop making more products and I stop using up any of my other reactants. So the limiting reactant controls everything. And remember, limiting makes less is the key way to doing it. Now, chemical reactions work the same way as recipes do. I ran out of flour, so it looks like flour was my limiting reactant. Once I made 3 cakes, I was done with flour. So therefore I stopped using butter and I stopped producing cakes. Oh, and one other concept here, while I'm looking at limiting reactant, the other reactant or reactants are what we call excess reactants because we have too much. We have them in excess. So one of my reactants, based on the information given, is my limiting reactant. All of the rest are excess reactants. So flour in this case was the limiting reactant, and butter, salt, and sugar were excess reactants. Now, how does it apply to a real chemistry problem? Well, we still need a recipe. That's our balanced equation. And we still need how much we've got. That's always going to be given to you, 2.5 grams of hydrogen and 3.40 grams of oxygen. And since masses and moles, not all substances have the same molar mass. And the balanced equation says we use these things at different rate. So don't look at this and say, oh, I have less hydrogen. Hydrogen's my limiting reactant. That has nothing to do with it. Remember, you have to do the evaluation here. Now, what I'm really doing is the limiting makes less idea. To find out my limiting reactant, what controls the reaction, I've got to find out what's my limiting reactant. Is hydrogen or is oxygen my limiting reactant? Now, to do that, I'm going to use the limiting makes less idea. Whichever one makes less water has to be my limiting reactant. So I'm going to start with 2.50 grams of hydrogen, and I'm going to predict how many grams of water I could make. Now, in this particular case, it's like any stoichiometry problem. I'm going to start with the middle. I don't want hydrogen, so moles of hydrogen go on the bottom. I want water, so moles of water go on top, and my numbers come from the balanced equation. Then I ask myself, do I need my first and my third steps? Well, every time I see moles, I lose a step. I don't want moles, and I'm not given moles, so I'm not going to lose any step. And both of these deals with mass, so I'm going to use molar mass in my first and third steps here. So I got to get from grams of hydrogen to moles of hydrogen. And like all molar masses, it's the mass in grams from the periodic table, and it's 1 mole. So 1 mole of hydrogen, well, H is 1.0, so H2 is 2.0, and that's in 1 mole. Now, in step 2, I'm going from moles of hydrogen to moles of water, so I'm in moles of water, but I want grams, so I'm not done. So I got to get rid of moles of water and get to grams of water, and this one we've done tons of times. 1 mole of water is 18.0 grams of water. 2 1.0 is plus to 16.0, 18.0. So when I plug my numbers in my calculator, 2.5 times 2 times 18 divided by 2.0 divided by 2 hit equal. And notice I'm going to round to 2 sig figs here because I've got 2.0 grams there, and that's only got 2 sig figs. 2.50 had 3, 18.0 had 3, and all the rest of the numbers were exact, so they're unlimited. So I've got 2 as the least. Now, be careful. Some of your math or chemistry teachers will say, well, you start with 3, so end up with 3. Technically, they're wrong, but if that's what they're telling you to do it, they're grading your papers, go to 3. But we limited our hydrogen to 2.0 grams. We could have gone to more decimal places there at the periodic table. We rounded it to 2. I limited my significance, so I got to round it to 2. So I got 23 grams of water. Now, I'm not done because all I did was figure out how much water that many grams of hydrogen made. And I don't know if I used up all my hydrogen. So I have to turn around and do the same thing using the oxygen. If I have 3.40 grams of oxygen, how many grams of water can I make? And keep in mind here, always go to the same thing. So if I had water and CO2 as my two products, doesn't do them any good to find out how much water my hydrogen can make and how much CO2 my oxygen can make. Go to a common product so you can compare. Not a problem here because I only have one reactant, so all I can do is predict, or one product. So all I can do is predict how much water I've got. Now you tackle it the same way. I don't want moles of oxygen because I don't want oxygen. I want water, so I got to go to moles of water. And from the balanced equation, 1 mole of oxygen is 2.0 moles of water. And since I'm starting in grams and ending in grams, I got to do the first and third, and those are going to end up molar mass steps. For every 32.0 grams of oxygen, I have 1 mole. And that gets me from grams to moles of oxygen, and then I can go from moles of oxygen to moles of water, but I want grams of water. So I got to get rid of moles and go to grams. And we just looked at this last problem. It's 18.0 grams per 1 mole. So if you really think about it, yeah, I'm doing 2 3-step problems, but what I've got here in both problems is the exact same thing. I just have a beginning first half that's new. The last second half is always going to be the exact same thing. So it goes pretty quick when you actually do it. Now, as far as math, 3.40 times 18.0 times 2 divided by 32.0, rounded to 3 sig figs, is going to give me 3.83 grams. Whoa, that's a lot less than 23 grams. So that must mean I have too little oxygen to make a whole bunch of water. So that means O2 is going to be my limiting reactant because oxygen made less, so O2 is a limiting reactant. And I have found out something else useful. How much water can I actually make? Well, I did the prediction. 3.83 grams of water is how much water can I make. And the third thing, what is my excess reactant? Well, that looks like it's the hydrogen. So hydrogen would be the excess reactant. Now, the next type of limiting reactant problem is a little more difficult than that. If you're just finding the limiting reactant and how much of a product you can make, predict that product from each of your reactants. Yeah, it's going to be two-step problems, but you'll quickly find the limiting, the excess, and how much of that product you can make. But what happens if the question says, not how much water can I make and what's the limiting reactant? What happens if it says, how much of my excess reactant is left over? Well, we haven't really looked at doing that type of math. So before we get into it for the chemistry problem, we're going to go back to a recipe to see the idea. Because if you can picture it with a recipe, you can do the same mathematical stuff with chemicals. So remember, From our cake example, flour controlled the reaction was our limiting reactant, and we could only make 3 cakes because we ran out of flour. So that means I'm going to have butter and salt and sugar left over. Well, how would I find out how much is left over? Well, it's controlled by the limiting reactant because the limiting reactant controls everything, controls how many cakes I could make, but it also controls how much butter, salt, and sugar I use, and therefore how much butter, salt, and sugar are left. Now, to go about doing this, it's going to take us 2 separate math problems. Neither one is very hard here. You may already see what the answer is, so you may intuitively get the 2 math problems. So if I want to know how much butter is left over, recognize I first have to find out how much butter was used. Then I subtract to find out how much is left. So it involves 2 separate problems. And remember, flour controls how much butter we use. So my limiting reactant, I had 6 cups of flour. That's going to control how much butter I use. So how much butter did I use in getting rid of my 6 cups of flour? That's what I'm looking at here. So I don't want cups of flour, I want cups of butter. And the recipe says for every cake I needed 2 cups of flour, and for every cake I only needed 1 cup of butter. So the equality here is I use up cups of flour at a rate of 2 cups per cake, and I use up butter at the rate of 1 cup per cake. So the equality would be 1 cup of butter used is equivalent to 2 cups of flour used. So 6 times 1 divided by 2, I use 3 cups of butter. So the first part, finding out how much was used. Remember, that's the dimensional analysis part. The second part, how much is left, which is really what I want to find as my final answer. That's a subtraction. I had 4 cups of flour to begin with. That was what was in the cupboard. I just figured out I used 3 cups. There's going to be 1 cup of butter left over. So that's what's going to go back away as 1 cup of butter. Well, remember, chemical reactions work the same way. So going back to this problem, we figured out a second ago that 2 cups are, get back out of recipes and get back into chemistry here, that 2.50 grams of hydrogen made 23 grams of water, and 3.0 grams of oxygen could make only 3.83 grams of water. So I could only make 3.83 grams of water, and oxygen was my limiting reactant, and hydrogen was my excess reactant. So I know how much hydrogen, or I should say, I know how much oxygen I used. I used all of it. Oxygen was my limiting reactant, so I ran out of oxygen, and there's none left. But I do know hydrogen is my excess reactant. I just haven't done any calculation anywhere that tells me how much hydrogen I did actually use. Because remember, this 23 grams here is useless to do anything. You never use that for anything in our stoichiometry problem because we didn't have enough hydrogen to make all that water. So we don't do anything mathematically with that number. What we really have to do is recognize that oxygen is my limiting reactant, just like flour is my limiting reactant, and that's going to control how much hydrogen I used. So to find out how much hydrogen is left over, first I have to find out how much hydrogen was used up by using all of my 3.40 grams of oxygen. And then second, I can subtract from how much hydrogen I had. I know I had 2.50 grams. I just have to find out how much of that I used so I can subtract from it to find out what's left. So first is my stoichiometry part. I'm going from my limiting reactant mass to my excess reactant, which was hydrogen. So I want to find out how much grams of hydrogen I used. Like all stoichiometry, go to your middle step first. I don't want oxygen, so moles that are going to go on the bottom. I want hydrogen, so moles that go on top. And then for my balanced equation, 2 moles of hydrogen for every 1 mole of oxygen. Once again, first and third step, yes, I need them because neither one is dealing with moles. So first I get a molar mass problem. I don't want grams of oxygen, I want moles of oxygen. And I've got 32.0 grams for every 1 mole. I don't want moles of hydrogen, I want grams of hydrogen. And in 1 mole of hydrogen, I have 2.0 grams of hydrogen. So 34.0 times 2 times 2.0 divided by 32.0, going to 2 sig figs here, once again because of the 2.0 grams, is 0.43 grams of hydrogen. Now keep in mind, if your teacher says you got to go to 3 because you started with 3, they're wrong, but do it their way. Find out what really is. So it might be 0.426. I don't know. Do the math. I just rounded it here to 2. Now remember, that's how much I used. Well, I started with 2.50 grams, and I just figured out I used 0.43 grams. So subtract 0.43, round to correct sig figs, which would be 2 decimal places here, since they're both uncertain to 2 decimal places. I got to round to 2. So my calculator answer, dead on right rounded answer. I'm going to have 2.07 grams of hydrogen left over. So remember, to find out how much of an excess is left, first find out how much the excess is used in stoichiometry, then do a simple subtraction. So 2 things. Find out how much was used. That's my stoichiometry from limiting to excess. Go from massive limiting to massive excess every single time. And then subtract how much excess you had from what it started with. And that ends my third set of notes over stoichiometry, applications of stoichiometry known as limiting reactants.